Alright, so in the last video we started with the matrix A and we found the eigenvalues and placed them on the column D, which is just a diagonal function. So we have eigenvalue 1 equals to 0 and eigenvalue 2 equals to 5. And then we calculated the eigenvectors using the following formula. So A minus lambda I times the eigenvector V equals 0. And we found the two eigenvectors. So this one corresponds to the eigenvalue 0 and this one corresponds to the eigenvalue 5. And we decided that this was the best form that we can represent all of the values as integers. So this is our matrix B, and now what we want to do is we want to find a to the power of 100. So what we're going to do in this case is the following. We're going to have P d raised to the power of 100, as we discussed in the last video, times P inverse. Now what is P inverse? P inverse we can easily find using Octave. But just to give you a little recap of what this is, we're going to use row reduction here. So we're going to start with 2 minus 1, 1, 2. And then we're going to have the identity matrix in the other side. And as we discussed in previous videos on how to perform inversion using this row reduction scheme, what we're going to do is we're going to try and get an identity matrix on this side by performing only operations on the rows, by either subtracting or adding rows or multiplying one row by a constant. So the first thing we can do is we can get row 2 and we can multiply by 2 essentially. So we're gonna get 2 1 1 0, and then we're gonna get minus 2 2 0 2. Sorry, this should be 4 here, not 2. So this is the first change we can get. Now for the second operation, what we're going to do is we're going to have R2, so row 2 is going to be R2 plus R1. So we're gonna add this row to this row, so we're gonna get 2 1 0 5, then 1 0 1 2. Essentially we're just getting a 0 here, so that then we can get our pivot elements. Now here we can multiply by some constants, so let's have R2 equals to 1 over 5 R2, and then R1 equals to 1 over 2 R1. So we're just dividing each one by a different constant, so we're going to have 1 0 0.5 0 0.5 0, and then at the bottom we're going to have 0 1, and here we're going to have 0 0.2 and 0 0.4. And then finally let's have R2 is R1, oh sorry, this should be R1 minus half of R2. So this is going to be this row minus half of this, so that's going to be 1 0 0 1. Then we're going to have 0 0.4 minus 0 0.2, then 0 0.2 and 0 0.4. So this right here is going to be our P inverse. So now we have that, we can set up our equation as, so I'm just going to go back to the top. I'm just going to go back to the top. So we're going to have this equals to 2 minus 1 1 2 times this matrix. So remember, when we have a diagonal matrix, all we do is we just raise the eigenvalues to that power. So we're going to have 0 0 0 5 to the 100. Then we're going to get 0 0.4. This is our inverse matrix for P. Let me just erase this. And then we're going to perform the multiplication this way. So we're going to start with these elements and then move on to these elements, and that will make things easier for us. So we're going to have 2 1 minus 1 2. Then on this side we perform row-wise times column-wise operations. So we're going to get the following two values, 0 0 0.2 times 5 to 100, so those are really large values. I'm just going to write it in exact form for now, times 5 to 100. And hopefully from this you can see that you get the following. Sorry, just need to keep erasing here. So we're going to get the following matrix, and this is going to be 0.2 times 5 to 100, 0.4 times 5 to the 100, then the same here, and then if we write this in scientific notation, this is going to turn out to be 10 to the 69 times the following values, 1.5777, and I'm using 4 decimal places here. This is going to have very a lot of decimals as well, 3.1554, and then 6.3109. And this is our matrix. This is what our value of a to the power of 100 is. So we found it using this method of diagonalization. And diagonalization is all about finding a diagonal matrix which is composed of the eigenvalues of A, and then a matrix B which is composed of the eigenvectors of A, and then we put it in this form, and that allows us to find the power of matrix very easily. Now, how could we have done this using Octave? Well, it's very simple really. All we need to do is we input our matrix A first. So our matrix A was 1, 2, 2, 4. Now, what we can do is we can obviously find the eigenvalues and eigenvectors of that, just to make sure we're going to perform that operation here. So the best way to do this is to set up a matrix composed of 2 elements. So the first one we're going to call V for eigenvectors, and the second one lambda for eigenvalues. Set this equal to eigenvalues of A. So eig_A, that's the function that we need to use. And this gives us the following. So it gives us the eigenvalues in the form of a diagonal matrix, which is the same matrix as DS we have. So we have eigenvalue 1, 0, eigenvalue 2 is 5. And it gives us the eigenvectors, so column vectors in this form. And you will immediately notice that this is different from what we had originally. And we might wonder, why is that? Well, essentially what this program, and this is something MATLAB does as well, is it is using a different definition of what the values of the best reduction it can do. Instead of representing it as integers, it represents it as normalized quantities. So basically, the program has a built-in function that tells it to normalize it so that all the quantities are between -1 and 1. So essentially, this is why this is displayed in this form, rather than our usual, the values that we got here for eigenvectors, which were 2, -1, and 1, 2. And you'll notice that essentially these are the same quantities, because if you multiply this by 2, then it gives you this value. So that's the same as multiplying that quantity by 2. And they just chose the negative sign here because it was just more convenient. It just depends on the order in which you solve the equations using row reduction. But essentially, we notice that we get similar quantities. That what matters here is just the ratio between between the elements. That's the really important thing with eigenvectors. And as you just saw, these eigenvectors here are essentially equivalent to this one. So don't get too stressed if you find that they look a bit different on the program as how you found them manually. Because in the end, what we're going to have is, let's have the matrix A to the power of 100 and see if we get the same value. So let's go back down. And is this the same value? Well, we have these values here with the decimals, yes, and times e to the power of 69. So e here represents 10 times 10 to the power of 69. So yes, this is exactly the same value we got here. So this is just how you would go about it, finding in Octave. And you can see that this is really easy. You just input your matrix, and then from that you can get your eigenvalues and eigenvectors. And then you can perform this kind of operation directly. So this is a really, really nice thing about Octave and MATLAB and numerical computational software in general. You can perform these operations very easily. So just to give you an idea, we can extend this to larger matrices. So for example, if we had a 4 by 4 matrix, so 4 by 4, then you would expect that our characteristic equation would have, so the determinant equals 0 would allow us to find a quadric polynomial, which means that we will have something like a lambda 4 plus b lambda 2 power 3 and so on equals to 0. So this would be the characteristic polynomial. So the size of the matrix, the dimensions of the matrix, tells us the number of eigenvalues that we'll have. So if we have a 4 by 4 matrix, we'll have 4 eigenvalues, which corresponds to the 4 roots of this polynomial. And that's a concept that extends to n by n matrices. We're going to have n eigenvalues. And similarly, we're going to have n eigenvectors. Each one of them is going to correspond to a different eigenvalue. And then by doing that, we can essentially perform a lot of operations with this. But in general, this is really useful for this kind of operation. And in the next video, I'm going to go through another application of eigenvalues and eigenvectors, which is useful for solving systems of linear differential equations. So that's what we will do in the next video.